For thousands of years, one assumption has quietly shaped the way we picture the universe, whether we are looking at an ancient star map, a globe, or a photograph of a distant galaxy. We naturally expect every great structure to possess a middle. Every city has a center. Every wheel turns around a hub. Every circle has a point from which all distances are measured. It feels almost impossible to imagine anything different. The universe, surely, must be the same. Somewhere, perhaps unimaginably far away. There must exist a place that could honestly be called the center of everything. A location from which the cosmos began its expansion, where distances are smallest in one direction and greatest in another, even if no spacecraft could ever reach it. Many people quietly assume that such a place must exist. It is an idea so deeply rooted in everyday experience that questioning it feels almost unnatural. Yet modern astronomy gently suggests something remarkable. The universe appears to have no center at all. Not merely that we have failed to find one, not that it remains hidden beyond our telescopes, but that, according to our best observations and the mathematical framework that describes the expanding cosmos, no unique central location exists anywhere. At first hearing, this sounds less like science and more like a contradiction. How can something expand if there is nowhere from which it expands? How can galaxies move away from one another if there is no point they are moving away from? If the universe had a beginning nearly 14 billion years ago, shouldn't there be a place where that beginning happened? These questions are not signs of confusion. They are exactly the questions astronomers themselves had to confront. For centuries, humanity's picture of the cosmos steadily moved outward. The Earth lost its privileged position. The Sun became one ordinary star among hundreds of billions inside the Milky Way. Then the Milky Way itself became one galaxy among hundreds of billions more scattered across the observable universe. With every discovery, our cosmic address became less special. Yet even after surrendering our central place among the stars, many of our intuitions quietly survived. If Earth is not the center, perhaps the Milky Way is. If not the Milky Way, perhaps the local group. If not our galactic neighborhood, perhaps somewhere beyond all the galaxies lies the true middle of existence. Our minds continue searching for a center because every object we encounter in daily life possesses one. A mountain has a peak. A tree has a trunk. A whirlpool has an eye. Even an explosion has an origin from which debris flies outward. Everything in our experience teaches us that beginnings happen somewhere. The universe, however, is under no obligation to resemble the objects we see around us. Nature has repeatedly shown that the larger scales often behave in ways that feel deeply unfamiliar. Quantum particles ignore common sense. Black holes bend space itself. Time flows differently depending upon gravity and motion. Perhaps it should not surprise us that the universe as a whole also refuses to obey everyday intuition. Still, the idea remains difficult to accept. Picture a loaf of bread slowly rising inside an oven. As the dough expands, raisins embedded throughout it drift farther apart. From the viewpoint of any single raisin, every other raisin appears to be moving away. None of the raisins occupies the center of the expansion because the bread is not expanding outward from one raisin into empty space. Rather, the dough itself is stretching everywhere at once. The analogy is helpful, but only for a moment. Unlike bread, the universe is not rising inside an oven. There is no surrounding kitchen, no larger room into which the cosmos expands, no invisible container waiting beyond the galaxies. If space itself is expanding, then asking what lies outside the universe may be as meaningless as asking what lies north of Earth's North Pole. The question assumes a direction that may not exist. This realization leads to a subtle but profound shift. Perhaps we have been asking the wrong question, instead of searching for the center of the universe. Perhaps we should ask whether the concept of a center even applies. Throughout history, science has repeatedly advanced by recognizing that familiar words sometimes lose their meaning under extraordinary conditions. There is no universal up or down in space. There is no single universal now according to relativity. Could center belong to the same category? The answer did not emerge overnight. It arrived slowly, carried by generations of careful observations, patient measurements, and ideas that initially seemed almost impossible to believe. Astronomers did not simply declare that the universe has no center because it sounded elegant. They were led toward that conclusion because the evidence consistently pointed in the same direction. Every new telescope added another piece. Every improved measurement refined the picture. Every unexpected observation forced old assumptions to be reconsidered. Yet the deeper scientists looked, the stranger the puzzle became. If every observer, no matter where they are located among the galaxies, sees roughly the same large-scale expansion, then every observer might reasonably conclude that they occupy a kind of center. That cannot literally be true if center means a unique location, and yet the observations seem to insist upon exactly this peculiar symmetry. It is a paradox unlike those found in ordinary life, not because logic has failed, but because our intuition evolved in a world of rivers, forests, mountains, and horizons, not across billions of light-years of expanding space-time. The universe asks us to think beyond experience. It invites us to set aside the comforting geometry of familiar objects and consider the possibility that space itself follows rules unlike anything our ancestors could have imagined. This journey, however, cannot begin with distant galaxies or sophisticated equations. It begins much closer to home. Before we can understand why the universe may have no center, we must first understand why we have always expected one. The story starts with the sky as generations of human beings first came to know it, long before anyone realized that nearly every point of light overhead belonged to an unimaginably vast and evolving cosmos. Long before telescopes revealed the true scale of the cosmos, the night sky seemed remarkably simple. Every evening, the stars returned to familiar places, constellations rose in predictable seasons, the moon wandered slowly among them, while a handful of brighter objects, later known as planets, traced more complicated paths across the heavens, above every civilization, regardless of language or culture. The sky appeared dependable. It suggested order rather than chaos. To ancient observers, it was natural to believe that the universe had been carefully arranged around them. After all, wherever a person stood, the horizon formed a perfect circle. The stars appeared to rotate around a single point overhead. Day followed night with astonishing regularity. The sun rose from one horizon and disappeared beneath the other as though performing a journey designed specifically for those watching below. Nothing in ordinary experience hinted otherwise. This perspective shaped humanity's earliest models of the cosmos. In many ancient cultures, Earth occupied the center of creation. The heavens surrounded it like enormous transparent shells carrying the sun. Moon, planets, and stars in graceful circles. Different civilizations imagined different details, yet the underlying idea remained remarkably consistent. The observer stood at the center. Everything else revolved around that position. It is easy to dismiss these early ideas with the knowledge we possess today. But doing so would overlook something important. The geocentric universe did not arise because ancient people lacked intelligence. It arose because it matched what careful observation appeared to reveal. Stand beneath the stars on a clear night, and they truly seem to revolve around you. Walk 1,000 miles in any direction, and they still appear to revolve around you. Even today, without modern astronomy, few observations would immediately convince us otherwise. The sky offers an illusion so complete that it persisted for thousands of years. Eventually, however, tiny inconsistencies began to accumulate. The wandering planets occasionally slowed, stopped, and moved backward against the background stars before continuing their forward motion. These curious loops, known as retrograde motion, became increasingly difficult to explain within the simplest Earth-centered models. Astronomers refined their calculations. They added circles upon circles, creating intricate mathematical systems capable of predicting planetary positions with surprising accuracy. The models became more complicated because the observations demanded it. Then, gradually, another possibility emerged. Perhaps Earth was not the object everything else circled. When Nicholas Copernicus proposed that the planets, including Earth, orbited the Sun, the idea did more than simplify planetary motions. It quietly displaced humanity from the center of the known universe. The shift was philosophical as much as scientific. For the first time, people were asked to consider that what felt obvious might not be true. The Earth still seemed perfectly still beneath their feet. The sun still appeared to cross the sky every day, yet appearances could deceive. Over the following centuries, observations by astronomers such as Galileo Galilei, Johannes Kepler, and Isaac Newton transformed this revolutionary proposal into an increasingly coherent picture of the solar system. Earth became one planet among several. The sun became the organizing center of our local neighborhood. For a time, this new understanding restored a comforting sense of structure. If Earth was no longer central, at least the sun was. The universe still possessed a middle, only its location had changed. As telescopes improved, however, even this certainty began to fade. The Milky Way stretched across the night sky like a pale river of light. For centuries, its true nature remained mysterious. Was it a glowing cloud, a celestial pathway, a vast collection of distant stars? Gradually, astronomers realized that the Milky Way itself was an enormous stellar system containing hundreds of billions of stars, with our sun occupying no particularly distinguished location. Instead of residing near the middle, our solar system drifted quietly in one of the galaxy's spiral arms, roughly halfway between its center and outer edge. Once again, humanity found itself moving outward. The center had shifted beyond us, yet the galaxy still seemed to provide a satisfying answer. Surely this immense spiral island of stars represented something close to the heart of the universe. It was an understandable conclusion. After all, until the early 20th century, many astronomers believed the Milky Way constituted nearly everything that existed. The faint spiral patches visible through telescopes were often interpreted as nearby clouds of gas within our own stellar system. The universe still felt manageable, large, certainly, but not infinite. Then came another quiet realization. Those faint spirals were not clouds inside the Milky Way. They were galaxies in their own right, entire collections of stars comparable to our own, scattered across distances so immense that light required millions of years merely to travel between them. Suddenly, the Milky Way ceased to be the universe. It became one member of an immense cosmic population. The center moved yet again, or perhaps it disappeared altogether. This pattern is striking when viewed across history. Every time humanity believed it had identified the universe's central structure, new observations expanded the scale of reality. Earth yielded to the sun yielded to the Milky Way. The Milky Way yielded to a universe filled with countless galaxies. Each step made our cosmic address less unique. Yet an even deeper assumption remained untouched. Although our location became increasingly ordinary, we still pictured the universe itself as an enormous object, and every object we naturally believed possesses a center. A forest has a middle. A continent has a geographical center. A galaxy has a dense core around which stars orbit. Surely the universe, being the largest object of all, must possess one as well. The assumption feels almost unavoidable because our brains evolved to understand finite things. Every landscape we have explored has edges. Every building has a foundation. Every sphere has a center. Our everyday intuition quietly teaches us that these concepts apply everywhere. But what if the universe is fundamentally different from every object we have ever encountered? What if space is not something contained inside a larger arena, but is itself the arena in which everything exists? If that were true, many familiar ideas would need to be reconsidered. Distance would still have meaning. Direction would still exist locally. Galaxies could still move relative to one another. Yet the search for a universal middle might become as misplaced as searching for the easternmost point on a perfectly round Earth. The possibility is subtle enough to escape immediate notice. It does not announce itself through spectacular events or dramatic discoveries. Instead, it emerges quietly as observations accumulate, one after another, until an entirely different picture begins to take shape. The first hints of that new picture appeared not through philosophy, but through careful measurements of distant galaxies whose light carried an unexpected message across millions of years. What astronomers found within that ancient light would begin to fracture the last comfortable assumptions about where, or even whether, the universe has a center. For centuries, the universe appeared reassuringly stable. The stars returned each night. The constellations changed only with the seasons. Even when astronomers discovered that Earth orbited the Sun, and that our solar system occupied an unremarkable corner of the Milky Way, one assumption remained largely untouched. The universe itself seemed eternal. It was easy to understand why. Nothing in everyday life suggested that the cosmos could change on its larger scales. Mountains eroded slowly. Rivers carved valleys over immense spans of time, and civilizations rose and fell. Yet the heavens seemed almost perfectly permanent. The stars looked as though they had always occupied their places, and many believed they always would. A static universe felt natural. It felt complete. Even Albert Einstein initially shared this intuition. When he developed the general theory of relativity in 1915, he created an entirely new description of gravity. Rather than treating gravity as an invisible force pulling objects together, Einstein described it as the curvature of space-time itself. Massive objects such as stars and galaxies reshape the geometry around them, and other objects simply follow those curves. It was an astonishingly elegant theory. Yet when Einstein applied his equations to the universe as a whole, he encountered an unexpected problem. The mathematics refused to remain still. Gravity is attractive. Every galaxy pulls on every other galaxy. If the universe contained matter everywhere, then over time gravity should gradually draw everything closer together. His equation suggested that a universe filled with matter could not remain perfectly static. It had to evolve. Either it was expanding, or it was contracting. There seemed to be no stable middle ground. But this conclusion troubled Einstein. Like nearly everyone else, he assumed the universe itself was unchanging, rather than questioning that assumption. He modified his equations by introducing a new mathematical term known today as the cosmological constant. Its purpose was simple. It acted as a kind of gentle repulsion that exactly balanced gravity, allowing the universe to remain motionless on the larger scales. The equations became stable once more. The universe stood still, at least on paper. Meanwhile, another puzzle was quietly unfolding through increasingly powerful telescopes. Astronomers had begun studying mysterious spiral nebulae, faint swirls of light scattered across the sky. Some believed they were nearby clouds of gas inside the Milky Way. Others suspected they were something far larger. The debate became known as the Great Debate of 1920. At its heart lay a profound question: how large is the universe? If these spirals belong to the Milky Way, then our galaxy might encompass nearly everything that existed. If they lay far beyond it, then reality was vastly larger than anyone had imagined. The answer arrived through one of astronomy's most patient forms of investigation: distance. Unlike mountains or oceans, the universe offers no measuring tape. Astronomers must build a cosmic distance ladder, using one method to calibrate another. Nearby distances can be measured through parallax, the tiny apparent shift of stars as Earth orbits the Sun. Farther away, astronomers rely on special kinds of stars whose true brightness can be determined independently. Among the most valuable are Cepheid variable stars. These stars brighten and dim with remarkable regularity. More importantly, the length of their pulsation is directly related to their true luminosity, by comparing how bright they truly are with how bright they appear from Earth. Astronomers can estimate their distance with surprising accuracy. This relationship transformed the universe. In the early 1920s, Edwin Hubble began observing Cepheid variables inside the Great Spiral Nebula in Andromeda. Night after night, photographic plates accumulated. Tiny points of light slowly revealed their rhythmic changes. The calculations that followed carried astonishing implications. Andromeda was not inside the Milky Way. It lay more than 2 million light-years away, an entire galaxy comparable to our own. The universe instantly became incomparably larger. The Milky Way was no longer the universe. It was one island among countless others. This discovery alone fundamentally altered humanity's place in the cosmos. But another surprise was already waiting. Astronomers had long noticed that light from certain galaxies appeared slightly shifted toward the red end of the spectrum. This phenomenon, known as redshift, could occur for several reasons. A familiar example comes from sound. As an ambulance approaches, its siren sounds slightly higher in pitch. As it moves away, the pitch drops lower. The sound waves become stretched as the source recedes. Light behaves similarly. When an object moves away, its light waves become stretched, shifting toward longer wavelengths. Red. At first, these redshifts seemed like isolated curiosities. Then astronomers began comparing them with Hubble's new distance measurements. The pattern that emerged was extraordinary. The farther away a galaxy appeared, the greater its redshift tended to be. Distant galaxies were generally moving away faster than nearby ones. It was not a random collection of motions. It was systematic, orderly, almost universal. The relationship was so consistent that it eventually became known as Hubble's law. Distance and recession speed increased together. Every direction in the sky told essentially the same story. Galaxies were separating. The universe itself appeared to be expanding. This conclusion was almost impossible to absorb at first. After all, if galaxies were moving away from us in every direction, did that not imply we occupied the center? The idea seemed unavoidable. Stand in the middle of an explosion, and fragments fly outward all around you. Stand at the center of an inflating balloon, and every point moves away. Surely the expanding universe implied the same geometry. Yet something about the observations refused to fit this familiar picture. Astronomers studying distant galaxies in entirely different directions found remarkably similar patterns. If intelligent observers lived inside one of those remote galaxies, what would they see? According to the equations of general relativity, they too would observe other galaxies moving away in every direction. From their perspective, they would also appear to occupy the center. How could both be true? How could Earth seem central without actually being special? The paradox was subtle enough that many people overlooked it. Even today, the image of an explosion remains deeply persuasive because explosions occur inside space. They begin at one location and expand outward into surrounding emptiness. But what if the universe was not expanding into space? What if space itself was growing? That small change in perspective transformed everything. It suggested that galaxies were not racing through a pre-existing void from one central location. Instead, the distances between galaxies were increasing because the fabric of space itself was changing. The distinction is easy to state. It is much harder to truly understand. Over the coming decades, astronomers would gather more evidence supporting this extraordinary picture. Every new observation strengthened the same remarkable conclusion, while simultaneously making the mystery even deeper. If space itself expands everywhere, then perhaps asking where the expansion began is not quite the right question. And if that question is mistaken, what other assumptions about the universe might quietly be waiting to unravel? The history of astronomy is often told through discoveries. A new planet, a new telescope, a new equation. Yet some of the most profound changes in our understanding have not come from finding something new. They have come from realizing that familiar observations were telling a completely different story than anyone had suspected. The expanding universe belongs to this second kind of discovery. No one watched space begin to grow. No telescope captured a moment when the cosmos suddenly started stretching. Instead, astronomers assembled countless pieces of evidence, each seemingly modest on its own, until together they revealed a picture that was impossible to ignore. One of the remarkable aspects of this story is that the idea of an expanding universe did not begin with an observation. It began with mathematics. In the early 1920s, several physicists examined Einstein's general theory of relativity more closely than Einstein himself had initially done. Among them was the Russian mathematician and physicist Alexander Friedmann. Rather than insisting that the universe must remain static, Friedmann simply accepted what Einstein's equations naturally predicted. The result was surprising, depending on how much matter the universe contained and how that matter was distributed. Space-time itself could evolve. It could expand. It could contract. Its geometry could change with time. At first, these solutions attracted little attention. Mathematics alone was not enough. Without observational evidence, they remained elegant possibilities rather than accepted descriptions of reality. A few years later, an independent line of thinking emerged from an unexpected place. Georges Lemaître, a Belgian priest, astronome, and physicist, approached the problem from both theoretical and observational perspectives. Unlike many of his contemporaries, Lemaître was willing to take the redshift measurements of distant galaxies seriously, instead of treating them as isolated curiosities. He asked whether they might represent evidence that space itself was expanding. His calculations led him to a bold conclusion. The recession of galaxies could naturally arise if the universe itself were growing larger over time. In 1927, Lemaitre published this idea. His paper contained both theoretical reasoning and an estimate relating galaxy distances to their apparent recession speeds. Much of what later became famous as Hubble's law already existed within his work. Yet the paper appeared in a relatively obscure scientific journal and received little immediate recognition. The scientific world was not yet ready. Meanwhile, Edwin Hubble continued gathering observations with a 100-inch Hooker telescope at Mount Wilson Observatory, then the most powerful telescope on Earth. Night after night, enormous glass photographic plates captured faint galaxies whose light had travelled for millions of years before reaching California. Unlike modern digital detectors, every observation demanded patience. Exposure time stretched for hours. Measurements were made carefully by hand. Errors had to be checked repeatedly. Progress came slowly, but steadily. Hubble combined his increasingly reliable distance estimates with radial velocity measurements that had been collected by another astronomer, Vesto Slipher. Slipher's contribution is sometimes overshadowed by Hubble's name, yet it was indispensable. Years before Hubble determined galaxy distances, Slipher had painstakingly measured the spectra of dozens of spiral galaxies by examining tiny shifts in familiar spectral lines. He found that most of these galaxies appeared to be moving away from Earth. At the time, the significance of those measurements remained unclear. Without accurate distances, recession speeds alone revealed very little. Hubble's observation supplied the missing ingredient. When the two sets of measurements were brought together, an elegant relationship appeared. Nearby galaxies generally moved away relatively slowly. More distant galaxies receded more rapidly. The farther a galaxy lay from us, the greater its velocity appeared to be. The pattern was not perfect. Individual galaxies possess their own local motions caused by gravity. Some drift toward neighboring galaxies. Others orbit within clusters. These smaller movements create slight deviations. But once astronomers looked beyond nearby space, the larger trend became unmistakable. Distance and recession speed increased together. The universe behaved as though the fabric separating galaxies was gradually stretching. This distinction deserves careful attention. Galaxies are not primarily flying through space because of some colossal explosion that hurled them outward. Instead, modern cosmology describes the space between galaxies as expanding. The galaxies themselves participate in that expansion because the distances embedded within space-time are increasing. At first glance, this may seem like little more than a difference in wording. It is not. Suppose two small boats float on a calm lake. If one boat moves away by using its engine, it travels across the water, but if the lake itself somehow expanded, carrying both boats farther apart without either one moving through the water, the situation would be fundamentally different. The analogy is imperfect because lakes do not expand in this way. Still, it hints at an important distinction. The expansion of the universe is not simply motion within space. It is the evolution of space itself. To help communicate this unfamiliar idea, educators often turn to another comparison. Picture tiny dots drawn across the surface of an uninflated balloon. As the balloon slowly inflates, every dot sees every other dot moving farther away. No dot occupies a privileged position on the surface. Every location experiences the same overall pattern. An observer living on any one of those dots could reasonably conclude that everything else is receding from them. Yet no dot represents the center of the balloon's surface. The actual center exists only in the three-dimensional space surrounding the balloon. And here the analogy reaches its limit. Our universe is not believed to be the surface of a balloon expanding into some larger physical space. The comparison illustrates geometry, not reality. There is no observational evidence that the universe possesses an external center hidden in a higher dimensional environment. As far as current cosmology can determine, space itself is all the stage we have access to. The expansion occurs within that space-time, not into an observed outside. This subtle idea explains something that once seemed impossible. If every sufficiently distant galaxy appears to move away from us, that does not mean we occupy the center. Observers inside another distant galaxy would witness essentially the same pattern. Their measurements would produce a remarkably similar relationship between distance and recession. Both perspectives would be correct because neither observer sits at a unique location. The geometry itself produces the illusion of centrality. It is one of the rare situations in science where every observer can legitimately describe themselves as standing at the centre of what they observe, while no universal centre exists at all. By the early 1930s, this realization was becoming increasingly difficult to dismiss. Even Einstein eventually visited Hubble at Mount Wilson Observatory. After examining the accumulating evidence, he accepted that the universe was not static. The cosmological constant he had introduced to preserve an unchanging cosmos was no longer necessary for that purpose. The universe was dynamic. It had a history. It evolved. Space itself changed with time. Yet accepting expansion solved only one mystery. It immediately created another, perhaps even more profound than the first. If the universe is expanding today, then looking backward through time suggests that galaxies were once much closer together. Continue that reasoning far enough, and the entire observable cosmos seems to converge toward an unimaginably dense and hot early state. But if everything was once closer together, where exactly did that happen? At a single point somewhere in space, or everywhere at once? That question would lead cosmology into one of its deepest and most beautiful mysteries. By the middle of the 20th century, humanity's map of the universe had grown beyond anything previous generations could have imagined. The Milky Way was no longer the whole cosmos. It had become one galaxy among many. At first there were dozens, then hundreds, soon thousands. As telescopes became larger and more sensitive, those numbers climbed into the millions. Today, our best observations suggest that the observable universe contains hundreds of billions of galaxies, each holding millions, billions, or even trillions of stars. Yet the numbers themselves tell only part of the story. The true transformation came when astronomers began to see how these galaxies are arranged. From a distance, it is tempting to picture galaxies scattered randomly through space, like grains of sand tossed across a beach. Reality is far more intricate. Gravity, acting patiently over billions of years, has woven galaxies into structures of astonishing complexity. Our own home belongs to a modest gathering known as the Local Group. It contains more than 100 known galaxies, although only a few dominate the landscape. The Milky Way, Andromeda, the Triangulum Galaxy. The rest are mostly smaller dwarf galaxies quietly orbiting their larger companions. Even this neighbourhood stretches across roughly 10 million light-years. A beam of light leaving one side of the Local Group would continue travelling for millions of years before reaching the other. And yet, on the cosmic scale, the Local Group is merely a small village. Beyond it lies the Virgo cluster, home to well over 1,000 galaxies bound together by gravity. Beyond Virgo, a larger collection still. Galaxy clusters gather into superclusters. Superclusters connect through immense chains and filaments. Between them lie enormous cosmic voids, regions where relatively few galaxies reside. The resulting pattern has become known as the cosmic web. When computer simulations first began reproducing this structure, many astronomers were struck by its appearance. It resembles an enormous network of glowing threads, not unlike frost spreading across a window, or rivers branching across a continent, or the delicate filaments of a living cell viewed beneath a microscope. These similarities are visually striking, although they arise from entirely different physical processes. Nature often produces networks because simple rules, repeated across immense scales, can generate surprisingly familiar patterns. The cosmic web is one of the grandest examples. Its filaments stretch across hundreds of millions of light-years. At the intersections, gravity has gathered galaxies into enormous clusters. Within the vast empty regions between them, space remains comparatively quiet. If one could somehow drift through one of these immense voids, the night sky would appear profoundly different. Galaxies would be far fewer. The familiar band of neighbouring systems would largely disappear. Darkness would dominate. And yet even there, the expansion of the universe would continue. The geometry of space-time does not depend upon whether a region is crowded with galaxies or nearly empty. It unfolds everywhere. As astronomers charted larger and larger portions of the universe, another remarkable pattern slowly emerged. On smaller scales, the universe is undeniably uneven. Stars gather into galaxies gather into clusters gather into superclusters. The cosmos appears richly textured. But beyond a certain scale, something unexpected happens. The irregularities begin to average out. Viewed across hundreds of millions of light years, the universe becomes increasingly smooth. This idea is known as the cosmological principle. It is not a law of nature in the same sense as gravity. Rather, it is an observational conclusion supported by decades of increasingly precise measurements. According to this principle, when viewed on sufficiently large scales, the universe is homogeneous and isotropic. These two words describe different aspects of cosmic uniformity. Homogeneous means that the universe has roughly the same average properties from one place to another. No enormous region appears fundamentally different from another equally large region. Isotropic means that the universe looks approximately the same in every direction. Neither statement claims perfect uniformity. Galaxies, clusters, and voids clearly exist instead. They describe the universe after averaging over immense distances. The distinction is similar to looking at a forest from different heights. Standing among the trees, every direction appears unique. One path is shaded, another contains a stream, a third climbs a hillside. The forest feels highly irregular, but viewed from an aircraft thousands of feet above, the same forest begins to resemble a continuous green landscape. The individual differences remain real. They simply become less important at larger scales. The observable universe behaves in much the same way. This realization proved extraordinarily powerful. If the universe truly possesses no preferred direction and no preferred location on its larger scales, then every observer should witness essentially the same broad cosmic behavior. Our location is not privileged, nor is any other. This principle aligns beautifully with everything astronomers have measured, no matter where telescopes are pointed. Sufficiently distant galaxies reveal similar large-scale structures. No direction appears fundamentally special. Even the faint afterglow of the early universe, which astronomers would later discover as the cosmic microwave background, displays an astonishing degree of uniformity across the sky. Tiny variations exist. They are essential because they eventually gave rise to galaxies and clusters. Yet overall, the early universe appears remarkably smooth. This smoothness presents another puzzle. How did regions separated by enormous distances become so similar? The question would eventually inspire new ideas about the earliest moments of cosmic history. But even before those theories emerged, the observations themselves carried profound implications. Suppose you stand within one galaxy cluster. Everything beyond it appears to recede. Now suppose another civilization exists billions of light years away inside a completely different cluster. Their measurements would reveal the same pattern. Their surrounding galaxies would also appear to move away in every direction. Neither civilization occupies the center. Both simply observe the same expanding geometry from different locations. This conclusion feels increasingly unavoidable as the scale grows. The universe resembles no ordinary object. A galaxy has a center because gravity has pulled its stars toward a common region. A planet has a center because matter collapsed into a roughly spherical body. A hurricane possesses an eye because air rotates around a particular point. The universe, however, is not an object embedded inside something larger. It is the totality of observable space-time itself. Expecting it to possess a center may be asking it to behave like structures that exist within it, rather than recognizing that it belongs to an entirely different category. Yet one question remains stubbornly alive. If the large-scale universe has no preferred location today, what about the beginning, when cosmologists trace the expansion backward toward the hot, dense early universe? Are they following galaxies toward one ancient point, or are they uncovering something far stranger? The deeper scientists examined this question, the more they realized that understanding the beginning of the universe would require abandoning one final intuition inherited from everyday life. The intuition that every beginning must occur somewhere. Whether that assumption survives the next step of our journey is a question that has occupied cosmology for generations. By this point in our journey, one idea has slowly emerged from the evidence. The universe appears to be expanding. Galaxies become more distant over time. On the larger scales, no direction appears fundamentally different from any other. And yet one question continues to resist every simple answer. If the universe has been expanding for nearly 13.8 billion years, where did that expansion begin? It is an innocent question, Almost everyone asks it. Professional astronomers ask it. Students ask it. Children ask it. The difficulty is not the question itself. The difficulty is that the question quietly assumes something that may not be true. It assumes that the beginning of the universe happened at one location inside space. That assumption feels perfectly reasonable because every beginning we have ever witnessed takes place somewhere. A campfire begins at one spot on the ground. A flower blooms from one point in a garden. A volcano erupts from a mountain. Even the largest explosions humanity has ever produced originate from a single location before expanding into the surrounding environment. Our experience teaches us that every event has an address. The Big Bang seems as though it should have one too, but the deeper cosmologists explored this idea. The more they discovered that the universe refuses to fit the pattern of ordinary explosions. The phrase Big Bang is, in some ways, surprisingly misleading. It often conjures the image of an enormous fireball exploding into an empty void. One imagines a brilliant flash occurring somewhere in darkness, followed by galaxies racing outward through pre-existing space. It is a powerful mental image. It is also not what modern cosmology describes. According to the standard cosmological model, the Big Bang was not an explosion that happened inside space. It was the early evolution of space itself. This distinction changes everything. Suppose someone asks where the surface of the Earth begins. The question sounds unusual because the Earth's surface does not originate from one special point. Every location belongs equally to the surface. Likewise, when cosmologists describe the earliest observable state of the universe, they are not describing matter exploding away from one privileged location. They are describing a universe in which space everywhere was once much hotter, much denser, and much closer together. Every region participated, and there was no single cosmic address where the event unfolded while the rest of space waited nearby. The event occurred throughout the universe. This idea is so unfamiliar that it often feels unsatisfying at first. Our intuition keeps searching for the missing center. Surely, somewhere beyond what we can observe, there must be the original point. Yet every successful observation stubbornly refuses to reveal one. Wherever astronomers look, the large-scale universe appears statistically similar. No direction points toward an ancient birthplace. No enormous gradient suggests a central location. The expansion looks remarkably uniform. To understand why this matters, it helps to consider a simpler example. Imagine a vast sheet of graph paper. Every square on the sheet gradually becomes larger while keeping the same relative arrangement. If tiny dots are drawn at the intersections, each dot finds every neighbouring dot becoming more distant. No single square serves as the location from which the expansion began. The entire sheet changes together. This comparison is still incomplete because an actual sheet exists inside a room. The universe, as far as observations indicate, does not require an external room. Nevertheless, it illustrates a crucial point. Expansion can occur everywhere simultaneously without requiring a unique centre. General relativity naturally allows precisely this behaviour. Its equations describe the geometry of space-time itself. When cosmologists solve those equations under the assumption that the universe is homogeneous and anisotropic on large scales, the result is not an expanding cloud moving through space. It is an expanding space-time. Distances themselves evolve. This realization solved one mystery while creating another. If the Big Bang happened everywhere, then what exactly does everywhere mean? Did the universe begin as an infinitely large space that was simply much denser? Or was all of space once unimaginably compact? The answer depends on something we still do not know with certainty. We do not yet know whether the universe as a whole is finite or infinite. This distinction is subtle but profound. The observable universe is finite. Light travels at a finite speed because the universe has existed for a finite amount of time. We can observe only a limited region surrounding us. Beyond that cosmic horizon may lie vastly more space whose light has not yet had time to reach Earth. Perhaps the universe extends forever. Perhaps it curves back on itself in a way that makes it finite but without an edge. Current observations strongly suggest that space is extremely close to geometrically flat. But whether it is truly infinite remains an open scientific question. Whatever the ultimate answer, the absence of a centre remains. Even a finite universe need not possess a unique central location. The surface of a sphere provides a familiar illustration. It has a finite area. One can travel across it indefinitely without encountering an edge, yet no point on the surface qualifies as its centre. The centre of the sphere exists in a higher dimension, not on the surface itself. Cosmologists use this comparison carefully because our universe is not literally the two-dimensional surface of a sphere. Still, it demonstrates that finite does not necessarily mean centered. Many of the most successful models of the universe share this surprising property. As astronomers gathered increasingly precise observations throughout the late 20th century, the evidence continued pointing toward remarkable uniformity. Radio telescopes mapped distant galaxies. Spacecraft measured faint cosmic radiation. Large surveys charted the distribution of millions of galaxies. Again and again, the same conclusion emerged. No preferred location announced itself. No hidden middle gradually appeared. Instead, the universe behaved as though every sufficiently distant observer occupied an equally ordinary place. This is one of the most beautiful consequences of the cosmological principle. It is also deeply humbling. Human history has often involved surrendering privileged positions. Earth is not the centre of the solar system. The Sun is not the centre of the galaxy. The Milky Way is not the centre of the universe. Now, cosmology invites one more step. Perhaps the universe itself has no centre to occupy. And yet this elegant picture carries its own unresolved tension. If the early universe was so remarkably uniform, how did it eventually produce galaxies, stars, planets, and ultimately observers capable of asking these questions? The cosmos clearly began with extraordinary smoothness. Somehow, tiny irregularities grew into everything we see today. Understanding how that happened would require looking even farther back, toward the earliest measurable light in existence. That ancient light still fills the universe today, carrying a message from a time when the first great mystery had only just begun to unfold. For much of human history, the universe could only be studied by looking at points of light scattered across the darkness, stars, planets, occasionally a faint cloud that later proved to be another galaxy. Everything astronomers knew had to be inferred from the light arriving at Earth. That remains true today. Even our most advanced observatories cannot travel to distant galaxies. They cannot collect pieces of ancient stars or measure the temperature of remote regions directly. Nearly everything we know about the universe comes from decoding light that has crossed unimaginable distances. In many ways, astronomy is less the study of objects than the study of messages. Every photon carries information. Its color reveals temperature. Its brightness hints at distance. Its spectrum uncovers chemical composition. Its polarization tells us about magnetic fields. Even its arrival time preserves clues about events that occurred billions of years ago. The farther we look into space, the farther we look into time. This simple fact changes the way astronomers investigate the universe. When sunlight reaches Earth, it is about 8 minutes old. The light from Jupiter left roughly 40 minutes earlier. The glow of Neptune began its journey more than 4 hours before arriving. The nearest star beyond our Sun appears as it was over 4 years ago. The Andromeda Galaxy has seen more than 2 million years in the past. Some galaxies observed by the James Webb Space Telescope appear as they existed only a few 100 million years after the universe became transparent to light. Astronomy is not merely observing distant places, it is reading different chapters of cosmic history simultaneously. This remarkable ability allowed astronomers to test whether the universe truly behaves the same in every direction. If there were a cosmic center somewhere within the observable universe, its influence might gradually reveal itself. Galaxies could become denser in one direction. Expansion might proceed more rapidly on one side of the sky than another. Ancient light might carry subtle asymmetries pointing toward a privileged location. Instead, the opposite emerged. The deeper observations became, the more uniform the universe appeared. One of the most powerful pieces of evidence arrived almost by accident. In the early 1960s, 2 radio astronomers, Arne Penzias and Robert Wilson, were working with a large horn-shaped antenna designed for sensitive microwave observations. They encountered an irritating background signal. No matter where they pointed the instrument, a faint microwave glow remained. They considered every possible explanation: electronic interference, nearby cities, instrumental errors, even pigeons nesting inside the antenna. Everything was carefully investigated and eliminated. The signal remained, unknown to them. Another group of physicists nearby had been searching for precisely such radiation. If the early universe had once been extremely hot and dense, then as space expanded and cooled, the leftover heat should still fill the cosmos today. Not as visible light, not as infrared radiation, but as an extraordinarily faint microwave glow spread almost perfectly across the entire sky. The mysterious signal was exactly that. Today it is known as the cosmic microwave background, often abbreviated as the CMB. It represents the oldest light humans have ever observed, not because it is infinitely old, but because before its release, the universe was too hot and dense for light to travel freely. For roughly the first 380,000 years after the Big Bang, matter existed as a glowing plasma of charged particles, photons scattered continuously from electrons. The universe resembled a brilliant fog. Only after expansion cooled the plasma enough for electrons and atomic nuclei to combine into neutral atoms could light finally move across space without constant interruption. The photons released during that transition have been travelling ever since, over nearly 13.8 billion years of cosmic expansion. Their wavelengths stretched enormously. Visible light gradually became microwaves. Their temperature cooled to only about 2.7 degrees above absolute zero. Yet they still fill every direction of the sky. The cosmic microwave background is astonishingly uniform. Measurements made by satellites including COBE, WMAP, and the Planck mission show that its temperature differs from one direction to another by only a few parts in 100,000. To appreciate how smooth this is, consider an ocean whose average depth differs by only a few millimeters across thousands of kilometers. Tiny variations certainly exist, but the overwhelming impression is one of extraordinary uniformity. This observation carries profound implications. If one side of the observable universe occupied a fundamentally different position from another, the ancient radiation should likely reveal it. Instead, every direction appears remarkably similar. The CMB does contain slight irregularities. These tiny fluctuations are not flaws. They are among the most valuable measurements in modern cosmology. Regions that were just slightly denser than average contained a little more gravity. Over billions of years, those minute differences slowly attracted additional matter. The densest regions eventually formed galaxies, clusters, and the immense filaments of today's cosmic web. Everything visible around us grew from fluctuations so small that they would have been almost impossible to notice without exquisitely precise instruments. This is one of the universe's quietest miracles. The largest structures in existence emerged from differences almost too subtle to measure, yet the overall smoothness remained. The fluctuations appear randomly distributed across the sky rather than pointing toward a preferred cosmic direction. This supports the cosmological principle introduced earlier. On sufficiently large scales, every region of the observable universe behaves much like every other. Another line of evidence comes from galaxy surveys. Projects such as the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies across enormous volumes of space. These observations reveal breathtaking complexity on smaller scales. Clusters, voids, filaments, walls stretching hundreds of millions of light years. Yet once astronomers average across truly immense distances, the distribution becomes increasingly uniform. There is no obvious cosmic mountain rising above the rest, no universal valley, no hidden center around which all galaxies gather. Even the expansion itself follows the same pattern. Astronomers measure recession using many independent techniques. Type Ia supernovae serve as reliable distance indicators. Baryon acoustic oscillations preserve subtle patterns from the early universe. Gravitational lensing reveals how matter bends light across vast regions of space. Although each method has its own uncertainties and ongoing refinements, together they paint a remarkably consistent picture. The universe expands in a way that is largely the same no matter which direction we observe. This does not mean cosmologists believe every question has been answered. Far from it. Tensions remain. Some measurements of the universe's expansion rate differ slightly from others, a puzzle known as the Hubble tension. Whether this reflects unknown systematic errors, new physics, or something else entirely remains an active area of research. Science advances precisely because such disagreements are investigated rather than ignored. Yet none of these debates has uncovered evidence for a cosmic center. Instead, every new generation of observations strengthens an increasingly extraordinary conclusion. The universe behaves as though no place is fundamentally more central than any other. The evidence has become broad, independent, and mutually reinforcing. Ancient light, galaxy maps, supernovae, the geometry of space-time, each tells a different part of the same story. And yet, evidence alone does not automatically reveal the underlying explanation. Several ideas have been proposed to account for why the universe looks this way. Some have become central to modern cosmology, others remain speculative, distinguishing carefully between established observation, successful theory, and unresolved hypothesis is the next step in understanding why a universe without a center may be not only possible, but inevitable. One of the quiet strengths of modern astronomy is that it rarely depends upon a single explanation. Observations come first, theories come afterward. The best theories survive because they continue matching new evidence, while weaker ideas gradually fade as measurements become more precise. This process is especially important in cosmology. No scientist can place the universe inside a laboratory. No experiment can recreate billions of years of cosmic history. Instead, astronomers observe the universe as it is today, collect every available clue preserved in ancient light and distant galaxies, and then ask which explanations account for those observations most successfully. Along the way, it becomes essential to distinguish four very different kinds of scientific knowledge: observed facts, measured evidence, accepted theories, open hypotheses. These categories are sometimes blurred in popular discussions, but they serve very different purposes. An observed fact is something directly measured. Galaxies exhibit redshift. The cosmic microwave background exists. The universe contains vast networks of galaxies connected by enormous filaments. These observations are not assumptions. They have been confirmed repeatedly by independent instruments across many decades. Measured evidence goes one step further. When astronomers determine that more distant galaxies generally display larger redshifts, they are identifying a measurable relationship. When satellites reveal that the microwave background is almost perfectly uniform with tiny fluctuations, those measurements become evidence that any successful explanation must accommodate. Theories then attempt to explain why these observations occur. In science, the word theory does not mean a casual guess. It refers to a comprehensive framework that consistently explains many independent observations while making successful predictions. General relativity is such a theory. The standard model of cosmology, often called the lambda cold dark matter model, or lambda CDM, is another. Finally come hypotheses. These are ideas that remain plausible but have not yet received enough evidence to become widely accepted. Some eventually mature into established science. Others are abandoned as new observations arrive. Understanding these distinctions allows us to examine one of cosmology's greatest mysteries with appropriate humility. The observations strongly indicate that space is expanding. General relativity successfully describes how expanding spacetime behaves. The standard cosmological model reproduces an extraordinary range of observations. Yet questions remain. How exactly did expansion begin? Why is the universe so remarkably uniform? Why does space appear nearly flat? These questions have inspired multiple scientific ideas. Some are firmly established. Others remain under active investigation. The leading description of cosmic expansion begins with Einstein's equations. Rather than treating galaxies as objects moving through a fixed stage, general relativity allows the stage itself to evolve. Distances between widely separated galaxies increase because space-time expands. This framework naturally explains Hubble's observations without requiring Earth, the Milky Way, or any other galaxy to occupy a privileged position within this picture. Asking for the center of the universe becomes similar to asking which point on Earth's surface is most central. The geometry simply contains no preferred location. This theoretical framework has proven extraordinarily successful. It predicts how galaxies should recede. It explains gravitational lensing. It accurately describes the behavior of black holes, neutron stars, and gravitational waves. Each successful prediction strengthens confidence that general relativity captures something fundamentally correct about gravity. Yet even an enormously successful theory has limits. Einstein's equations describe the evolution of space-time after the universe becomes sufficiently well-behaved. They become increasingly difficult to apply under the extreme conditions thought to exist during the earliest moments of cosmic history. There, quantum physics almost certainly becomes important. Unfortunately, physicists do not yet possess a complete theory uniting general relativity with quantum mechanics. This missing bridge remains one of the great challenges of modern physics. Another influential idea emerged during the late 20th century, known as cosmic inflation. It proposes that the very early universe experienced an extraordinarily brief period of extremely rapid expansion. The expansion was astonishingly fast, not because matter travelled through space faster than light. Rather, space itself expanded so rapidly that enormous regions became separated by immense distances in a tiny fraction of a second. Inflation was proposed to solve several puzzling observations. One involves the remarkable uniformity of the cosmic microwave background. Regions located on opposite sides of the observable universe appear nearly identical, despite seemingly lacking enough time to exchange information at the speed of light. Inflation offers a possible explanation. Before the rapid expansion, those regions may once have been close enough to reach thermal equilibrium. The subsequent stretching then carried them far apart while preserving their similar properties. Inflation also helps explain why the observable universe appears so geometrically flat, just as the surface of an enormous sphere appears nearly flat when viewed across a small area. Sufficiently rapid expansion would make any initial curvature increasingly difficult to detect. Current observations are broadly consistent with this prediction, yet it is important to be precise. Inflation is a powerful scientific hypothesis supported by several lines of indirect evidence. Many cosmologists regard it as the leading explanation for multiple features of the universe. However, the exact physical mechanism responsible for inflation remains unknown. No experiment has yet directly identified the particle or field that would have driven it. Different inflationary models make slightly different predictions. Research continues. This distinction matters because science advances through careful uncertainty rather than absolute certainty. Alongside inflation, other ideas have been explored. Some cosmologists investigate bouncing universe models, in which cosmic expansion follows an earlier contracting phase. Others examine cyclic cosmologies involving repeated periods of expansion and contraction. Still others consider modifications to gravity itself or quantum descriptions of space-time that differ from conventional approaches. These alternatives remain active areas of research. Some address questions that inflation leaves unresolved. Others attempt to solve entirely different problems. At present, none has accumulated sufficient observational support to replace the standard cosmological framework. This does not mean they are wrong. It simply means the available evidence currently favours other explanations. An equally important mystery concerns dark matter and dark energy. Although neither directly determines whether the universe has a centre, both influence its evolution. Dark matter appears to provide much of the gravitational framework around which galaxies and clusters formed. Dark energy appears responsible for the accelerated expansion discovered during the late 1990s. Together, these invisible components constitute most of the universe's total energy content. Yet their fundamental nature remains unknown. Once again, observation has moved ahead of explanation. Astronomers can measure their effects with impressive precision. Understanding what they actually are remains an unfinished chapter. This is one of the most remarkable features of modern cosmology. The broad outline of the universe is understood with considerable confidence. Many of the underlying ingredients remain mysterious. The absence of a cosmic centre belongs to the first category. The ultimate explanation for every aspect of that geometry belongs partly to the second. Science is comfortable holding both truths simultaneously. The universe appears to have no preferred location. The evidence supporting that conclusion is extensive. Exactly why the universe acquired these particular large-scale properties is still being explored. And if our current understanding is fundamentally correct, then one extraordinary consequence follows naturally. Every civilization, no matter where it arises among the galaxies, would look outward and find itself surrounded by an expanding universe that seems to place them quietly at its own centre. There is a curious habit of the human mind. When faced with an unfamiliar idea, we instinctively search for an analogy. We compare the unknown with something we have already experienced. A map helps us understand a city. Ripples across a pond help explain waves. A flowing river helps us picture electric current. These comparisons are useful. They are also dangerous. Every analogy eventually reaches a point where it quietly stops resembling reality. Nowhere is this more apparent than in cosmology. If the universe truly has no center, then our ordinary experiences provide almost no direct comparison. Every object we have ever held, every landscape we have ever crossed, every building we have ever entered possesses a middle, an edge, or both. The universe appears to belong to an entirely different category. One way to appreciate this is through a simple thought experiment. Suppose there exists an observer living in a galaxy nearly 5 billion light-years from the Milky Way. Their civilization has developed radio telescopes, optical observatories, and space-based instruments every bit as capable as our own. They have measured the recession of distant galaxies. They have mapped the faint microwave glow left from the early universe. They have carefully calculated the expansion of space. Eventually, they reach a remarkable conclusion. Their galaxy appears to occupy the center of the expanding universe. At first, this seems impossible. After all, we have reached exactly the same conclusion from Earth. Surely both cannot be correct. Yet according to modern cosmology, both observers are describing reality accurately. Neither civilization occupies the center, because there is no universal center to occupy. Instead, each observer experiences the same expanding geometry from a different location. To understand why, picture standing in the middle of a vast crowd. Everyone begins walking away from one another at exactly the same proportional rate. The farther apart two people already are, the faster the distance between them increases. From your perspective, everyone moves away. From someone else's perspective, everyone also moves away from them. No person initiated the expansion. The entire pattern evolved together, unlike this crowd. However, galaxies are not consciously moving, nor are they walking across a cosmic floor. The distances between them increase because space-time itself changes. The thought experiment reveals something subtle. The appearance of centrality does not necessarily imply actual centrality. Perspective can create patterns that feel absolute while remaining entirely local. Astronomy has repeatedly taught this lesson. For centuries, the sun appeared to circle Earth. The observation itself was real. The interpretation was incomplete. Likewise, every galaxy appears surrounded by expanding space. The observation is real. The temptation to identify that location as the unique center is the misunderstanding. Now consider another question. What if humanity somehow traveled billions of light-years across intergalactic space? Suppose future generations reached an unimaginably distant galaxy and established a new civilization there. Would they finally discover that Earth had left the center behind? Surprisingly, the answer appears to be no. From their new home, the expansion would again appear nearly identical. Galaxies would recede in every direction. The cosmic microwave background would still surround them. The large-scale universe would once again seem centered upon their own location. Nothing about the journey would reveal a hidden cosmic middle. This is one of the most counterintuitive predictions of the expanding universe. Changing position does not uncover a preferred location because the geometry itself contains none. Thought experiments like these are not proofs. They simply help us visualize what the mathematics and observations already indicate. Another illustration begins with a familiar object. Imagine reading a novel. Every chapter has a beginning. Every sentence has a first word. Every page has a top. These features are perfectly meaningful within the book. Now ask where the center of the story is. The question becomes more complicated. Is it the middle page? The emotional climax? The chapter where everything changes? Different answers become possible because the story is not a physical object in the same sense as its printed pages. The concept of center depends upon what we actually mean. Something similar happens in cosmology. When we ask for the center of the universe, we often fail to distinguish between different meanings of the word. Do we mean the center of all matter? The location where the Big Bang occurred? The midpoint of all observable galaxies? The geometric center of space? These questions sound similar. Scientifically, they are very different. The observable universe certainly possesses a center from our perspective. It is us. Not because Earth occupies a privileged cosmic position, but because every observer naturally sits at the center of their own observable horizon. Light travels at a finite speed. We can observe only the region from which light has had time to reach us since the early universe became transparent. This creates a spherical horizon surrounding every observer. If another civilization exists billions of light years away, they possess their own observable universe centered on their location. The two observable regions overlap only partially. Neither represents the universe as a whole. This distinction often causes confusion. The observable universe is not identical to the entire universe. It is simply the portion currently accessible to observation. Beyond that horizon may exist vastly more galaxies whose light has not yet arrived, perhaps infinitely more. Current evidence cannot determine the full extent. This limitation reminds us of something profound. There are questions that science cannot yet answer, not because they are meaningless, but because nature has not provided enough observable information. Whether the entire universe is infinite, whether space eventually curves back upon itself, whether other regions extend beyond our cosmic horizon forever. These remain open questions. Yet within everything we can observe, one conclusion continues to withstand every test. No preferred center emerges. Every successful measurement reinforces the same elegant picture. The farther we travel in thought, the less important our own location becomes. In many ways, this mirrors one of the deepest themes in the history of science. Progress has often involved recognizing that our perspective, while valuable, is not unique. The Earth is ordinary. The Sun is ordinary. The Milky Way is ordinary. Perhaps our place in the geometry of the universe is ordinary as well. And yet this realization does not diminish humanity's significance. If anything, it does the opposite. It suggests that the same physical laws governing our small corner of the cosmos operate across unimaginable distances. A civilization born around another distant star would study the same gravity, the same expanding space-time, the same ancient microwave background. They would inherit the same questions. Perhaps they too would spend generations wondering why the universe appears to place them gently at the center of everything they can see. The next step in our journey is to look beyond individual observers altogether. Instead of asking what any one civilization experiences, we will widen our view until galaxies themselves become tiny features within an even grander structure, revealing how the geometry of the universe shapes reality on the largest scales known to science. As our perspective rises ever higher above individual galaxies, a remarkable transformation begins to occur. The Milky Way. Once the entire universe in humanity's imagination becomes only a faint spiral among hundreds of billions of others, the local group shrinks into a tiny neighborhood. The great clusters of galaxies become scattered points connected by delicate filaments stretching across unimaginable distances. Eventually, even these immense structures begin to resemble threads woven into a fabric too vast for the eye to fully comprehend. It is at this scale that one of cosmology's deepest ideas becomes easier to appreciate. The universe is not simply filled with objects. It possesses geometry. Geometry is often introduced in childhood through triangles, circles, and straight lines drawn on paper. Later, it describes the shape of buildings, bridges, and planets. But geometry can also describe something much larger. It can describe space itself. This was one of Einstein's most profound insights. Before general relativity, space was usually imagined as an invisible stage upon which matter moved. Stars travelled through it. Planets orbited within it. Light crossed it. The stage remained unchanged. Einstein proposed something entirely different. Matter and energy influence the geometry of space-time. The stage is no longer fixed. It bends. It stretches. It evolves. Gravity is not simply an invisible pull acting across empty space. Instead, gravity reflects the changing geometry of space-time itself. This idea can feel abstract until we notice how often geometry determines movement in ordinary life. Airplanes flying between distant cities rarely follow straight lines on a flat map. Instead, they trace great circle routes across Earth's curved surface. To passengers looking out the window, the journey may seem indirect, yet those curved paths are actually the shortest possible routes across a sphere. The geometry determines the motion. The same principle operates throughout the universe. Planets orbit stars because space-time near the star is curved. Galaxies orbit within clusters because enormous concentrations of matter reshape the geometry surrounding them. Even light, which has no mass, follows these curved paths. This produces one of the most beautiful phenomena in astronomy: gravitational lensing. When light from a distant galaxy passes near a massive cluster of galaxies, the cluster's gravity bends the surrounding space-time. The light follows that curvature to observers on Earth. The distant galaxy may appear distorted into graceful arcs or even multiple images. No ordinary lens exists between us. The geometry itself acts as the lens. Modern telescopes have photographed hundreds of these extraordinary systems. Some reveal complete rings of light surrounding foreground galaxies. Others display elongated arcs stretching across enormous distances. These images are more than beautiful curiosities. They provide direct evidence that space-time possesses structure. Geometry leaves visible fingerprints across the sky. Yet gravity tells only part of the story. The geometry of the universe also determines how expansion unfolds. Here it becomes useful to distinguish between local and cosmic behavior. Within galaxies, gravity dominates. Stars orbit the galactic center. Solar systems remain intact. Planets do not gradually drift away from their stars because of cosmic expansion. Even neighboring galaxies can remain gravitationally bound. The Milky Way and Andromeda, despite the overall expansion of the universe, are actually moving toward one another. In roughly 4 to 5 billion years, they're expected to merge into a single larger galaxy. This may seem surprising after everything we have discussed. If the universe is expanding everywhere, why are these galaxies approaching each other? The answer lies in scale. Expansion is extraordinarily gentle over relatively short cosmic distances. Where gravity becomes sufficiently strong, it overwhelms the gradual stretching of space. Bound systems remain bound. Stars stay within galaxies. Galaxies remain within clusters. Only across the immense distances separating clusters and superclusters does expansion become the dominant influence. This distinction is essential because it reminds us that the universe operates through multiple processes simultaneously. Gravity gathers. Expansion separates. Neither process completely eliminates the other. Instead, they coexist across different scales. Computer simulations have become invaluable for exploring this delicate balance. Beginning with tiny fluctuations preserved in the cosmic microwave background, astronomers allow gravity and expansion to interact over billions of simulated years. The resulting structures resemble the observed universe with remarkable fidelity. Filaments emerge naturally. Clusters grow where matter accumulates. Vast voids expand between them. These simulations do not merely create attractive images. They test whether our theories correctly reproduce reality. When successful simulations resemble actual galaxy surveys, confidence in the underlying physical model grows. Yet the simulations also reveal something deeply philosophical. The large-scale appearance of the universe does not require a central architect arranging galaxies into place. Simple physical laws, applied consistently across immense spans of time, naturally generate astonishing complexity. This is a recurring theme throughout nature. Snowflakes develop intricate symmetry through straightforward molecular interactions. Sand dunes form elegant patterns through countless grains responding to wind. River networks emerge as water follows gravity across uneven landscapes. Likewise, the cosmic web grows from gravity acting upon tiny differences in density, while space itself continues expanding. Order arises gradually, not through design imposed from outside, but through the persistent operation of physical law. The geometry of the universe also influences a more subtle feature of reality. Our horizons, because light travels at a finite speed and because space expands while light is traveling, there exist regions whose signals have not yet reached us. Every year, our telescopes receive light that has spent billions of years crossing the cosmos, yet there are also regions so distant that their present-day light may never arrive. Not because the speed of light changes, it remains constant in a vacuum. Instead, the space between us and those regions expands rapidly enough that newly emitted light cannot overcome the increasing distance. This idea often feels unsettling. It suggests that parts of the universe may remain forever beyond direct observation, not hidden behind clouds, not blocked by dust, simply separated by the evolving geometry of space-time itself. In this sense, The observable universe resembles an island whose shoreline slowly changes with time. We continue discovering new regions as ancient light finally reaches us. At the same time, other regions recede beyond the possibility of future communication. Our cosmic horizon is not merely a limitation of technology, it is a consequence of the universe's geometry. As astronomers came to understand these immense structures, another realization quietly followed. Geometry alone could no longer explain every observation. Measurements toward the end of the 20th century revealed something unexpected. The expansion of the universe was not slowing under gravity's influence as many had anticipated. Instead, it appeared to be accelerating. Some additional ingredients seemed to be shaping the geometry of space-time itself. Whatever that ingredient might be, it promised to deepen the mystery of a universe that already seemed astonishingly difficult to comprehend. One of the quiet pleasures of astronomy is discovering that ideas which first appear unrelated often turn out to be deeply connected. A faint glow left over from the early universe, the graceful arc of light around a distant galaxy, the recession of galaxies across billions of light years, the distribution of enormous cosmic voids. At first, these seem like entirely separate phenomena, each belonging to its own chapter of astronomy, yet as observations accumulated throughout the 20th and 21st centuries, scientists realized they were all describing different aspects of the same evolving universe. The connections did not emerge all at once. They appeared gradually. Much like individual stars becoming visible as twilight fades, consider the cosmic microwave background. Earlier, we encountered it as the oldest light we can observe, released when the universe became transparent roughly 380,000 years after the Big Bang. At that time, the cosmos was astonishingly smooth. Temperature differences across the sky measured only a few parts in 100,000. Those tiny variations might seem insignificant. In everyday life, such small differences are almost invisible, yet gravity possesses extraordinary patience. Given enough time, even the slightest imbalance begins to matter. A region containing just a little more matter than its surroundings exerts slightly stronger gravity. That additional gravity attracts a little more material. As more matter gathers, gravity grows stronger still. The process feeds upon itself, not explosively, not rapidly, but steadily across billions of years. From these almost imperceptible differences emerged galaxies, galaxy clusters, the immense filaments of the cosmic web. Even the local group containing the Milky Way owes its existence to fluctuations so small they would have escaped every human sense. This realization links two observations that initially appear unrelated. The oldest light in the universe contains the seeds of its largest structures. The smooth early cosmos and today's richly textured universe are not separate stories. They are consecutive chapters of the same history. Another connection appears when astronomers examine gravity itself. Galaxies rotate far more rapidly than expected. If only visible stars and gas contributed to their gravity, many galaxies should gradually fly apart. Instead, they remain stable. Galaxy clusters reveal a similar mystery. Their visible matter provides nowhere near enough gravity to hold them together. Gravitational lensing strengthens this conclusion. Light bends far more than visible matter alone can explain. These independent observations converge upon the same idea. Something invisible contributes additional gravity. Today, this unseen component is called dark matter. The name is descriptive rather than explanatory. Dark matter does not simply refer to ordinary matter hidden in darkness. Instead, it represents a form of matter that appears to interact strongly through gravity, while interacting very weakly, if at all, with light. Astronomers have not yet identified its fundamental nature. No laboratory has conclusively detected the particles responsible. Nevertheless, its gravitational influence appears throughout the universe. Again, the important point is connection. Dark matter is not introduced merely to explain one puzzling galaxy. It helps explain galaxy rotation, galaxy clusters, gravitational lensing, the growth of cosmic structure, and subtle patterns preserved within the cosmic microwave background. Multiple independent observations point toward the same unseen ingredient. This convergence gives scientists confidence that they are describing something real, even if its identity remains mysterious. The universe often reveals itself through consistency. One clue alone may mislead. Many unrelated clues pointing toward the same conclusion deserve careful attention. The same principle applies to cosmic expansion. When Edwin Hubble first identified the relationship between distance and redshift, astronomers knew the universe was expanding. What they did not yet know was how that expansion changed over time. Gravity should gradually slow expansion. Every galaxy pulls upon every other. The universe resembles an immense collection of objects connected by mutual attraction. Many astronomers expected expansion to continue, but at an ever-decreasing rate. That expectation seemed reasonable. Then another connection emerged. By studying distant type Ia supernovae, astronomers found evidence that the expansion was not slowing as anticipated. Instead, billions of years after the Big Bang, the expansion began accelerating. The farther the universe evolved, the vaster large-scale distances increased. This unexpected result connected previously separate puzzles: the geometry of space-time, the future evolution of the universe, the distribution of galaxies, the age of cosmic structures. All appeared to require an additional ingredient. This mysterious influence became known as dark energy. As with dark matter, the name describes observations rather than providing a complete explanation. Scientists know its effects. They do not yet know its ultimate nature. Some possibilities relate to Einstein's cosmological constant. Others involve new physical fields or modifications to gravity itself. Research continues. Once again, cosmology demonstrates remarkable discipline. Observation comes first. Explanation follows carefully behind. Perhaps the most elegant connection of all concerns our original question: why does space appear to have no center? At first glance, this seems unrelated to dark matter, the cosmic microwave background, galaxy formation, or dark energy. In reality, every one of these subjects contributes to the same overall picture. The microwave background demonstrates remarkable large-scale uniformity. Galaxy surveys reveal no preferred direction. General relativity naturally describes expanding space-time without requiring a unique central location. Dark matter helps explain how structure formed within that expanding space-time. Dark energy influences how the expansion proceeds today. Together, these seemingly independent discoveries reinforce one coherent model. No single observation proves the universe lacks a center. Rather, dozens of independent observations fit comfortably within a framework where no preferred location exists. Science often advances in precisely this manner. Confidence grows not because one spectacular experiment settles every question, but because countless different investigations quietly agree. The pattern becomes increasingly difficult to dismiss. There is another connection that is less scientific, yet equally profound. Every major discovery in cosmology has gradually expanded our sense of perspective. The Earth was not the center. The Sun was not the center. The Milky Way was not the center. Now, even the observable universe around us is understood as merely one local perspective within a far larger reality. Each step has removed a privileged position while simultaneously revealing a richer universe than anyone had imagined. Paradoxically, the loss of centrality has made the cosmos more beautiful. A universe without a center is not less orderly. It is ordered differently. Its harmony arises from universal laws rather than preferred places. The same geometry operates everywhere. The same gravity shapes every galaxy. The same ancient light fills every direction. The same physical principles appear to govern regions separated by billions of light years. That remarkable consistency may be one of the deepest discoveries humanity has ever made. Yet consistency is not completeness. For every mystery that has been connected to another, new questions have appeared. Dark matter remains unidentified. Dark energy remains unexplained. The earliest moments of cosmic history remain hidden behind the limits of our current theories. Fortunately, astronomy is entering an era unlike any before. New observatories on Earth and in space are now capable of exploring the universe with extraordinary precision, offering fresh clues that may reshape our understanding once again. The story, it seems, is far from finished. For most of human history, the night sky changed very little. The same stars greeted every generation. The same constellations crossed the seasons. Progress in astronomy depended almost entirely upon patient observation and increasingly careful measurement. Today, however, astronomy has entered an entirely different era. Modern observatories do not simply look farther. They observe the universe in ways that previous generations could scarcely have imagined. Visible light is only a small part of the story. The universe also speaks through radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays, neutrinos, and even gravitational waves. Each messenger reveals a different aspect of reality. Together, they allow astronomers to study the cosmos with unprecedented depth. This transformation has become especially important in understanding the large-scale structure of the universe. One of the most significant advances arrived with space telescopes. Freed from Earth's atmosphere, these observatories avoid the constant blurring caused by turbulent air. The Hubble Space Telescope demonstrated this dramatically. Its images reached extraordinary clarity, revealing galaxies so distant that their light had begun its journey billions of years before Earth even existed in its present form. One of Hubble's most famous observations required no complicated target. Astronomers simply pointed the telescope toward what appeared to be an almost empty patch of sky. For days, Hubble collected light. When the images were finally combined, the empty region proved to contain thousands of galaxies. Some were relatively nearby, others lay so far away that their light represented some of the earliest chapters of cosmic history. The lesson was profound. The universe is far richer than human eyes can perceive. Every tiny region of darkness contains astonishing depth. More recently, the James Webb Space Telescope has extended that journey even farther into the past. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb specializes in infrared wavelengths. This capability allows it to detect galaxies whose light has been stretched by billions of years of cosmic expansion. Some of the earliest known galaxies have now been observed only a few 100 million years after the Big Bang. These observations are remarkable not simply because they are distant. They provide direct tests of cosmological theories. Computer simulations predict how the first galaxies should form. The telescope allows astronomers to compare those predictions with reality. Sometimes the agreement is excellent. Sometimes unexpected details emerge that require refinement. This continual dialogue between prediction and observation lies at the heart of science. Every successful prediction strengthens confidence. Every discrepancy becomes an opportunity to learn. Space telescopes are only part of this new picture. Across Earth, enormous surveys have begun mapping the three-dimensional distribution of galaxies with extraordinary precision. Rather than studying a handful of galaxies individually, astronomers now measure millions simultaneously. Each galaxy contributes 1 point within an immense cosmic map. When enough observations are combined, the familiar pattern of filaments, clusters, and vast voids appears with breathtaking clarity. These surveys have confirmed something increasingly important. On the larger scales accessible to observation, no preferred direction or preferred location emerges. The cosmic web extends throughout the observable universe without revealing a hidden center. Every new map reinforces the same conclusion. At the same time, astronomers have become increasingly interested in one subtle feature preserved within these maps: tiny ripples known as baryon acoustic oscillations. The name sounds technical, but the underlying idea is surprisingly elegant. In the early universe, matter and radiation formed an intensely hot plasma. Pressure waves traveled through that plasma somewhat like sound waves moving through air. When the universe cooled enough for neutral atoms to form, those waves effectively froze into place billions of years later. Their imprint remains faintly visible in the large-scale distribution of galaxies. These ancient ripples act as a kind of cosmic measuring stick. By comparing their apparent size at different distances, astronomers can determine how the universe has expanded throughout its history. Independent methods reaching similar conclusions are especially valuable. The expansion inferred from baryon acoustic oscillations agrees remarkably well with many other observations. Another revolution has come from gravitational wave astronomy. For centuries, astronomers relied almost exclusively upon light. In 2015, scientists directly detected gravitational waves for the first time. These tiny distortions of space-time were produced by merging black holes over 1 billion light-years away. The discovery confirmed another prediction of general relativity. More importantly, it introduced an entirely new way of observing the universe. Instead of seeing light emitted by distant events, Astronomers could now detect ripples travelling through space-time itself. As detectors improve, gravitational waves may eventually help refine measurements of cosmic expansion through what researchers call standard sirens, like standard candles such as Type Ia supernovae. These events allow independent estimates of distance. Each additional technique strengthens the reliability of cosmological measurements. Even computer simulations have become observatories in their own right. Using some of the world's most powerful supercomputers, scientists recreate billions of years of cosmic evolution. The calculations begin with conditions measured in the cosmic microwave background: gravity, dark matter, ordinary matter, and cosmic expansion then interact according to known physical laws. Over countless computational steps, galaxies emerge, clusters grow, filaments connect, voids expand, when the resulting structures resemble those observed by telescopes. Astronomers gain confidence that their understanding captures important features of reality. When simulations fail, the discrepancies become equally valuable. Nature has revealed that some ingredient remains incomplete. One of the most intriguing developments concerns the expansion rate itself. As measurements have grown increasingly precise, astronomers have encountered a subtle disagreement. Methods based on the early universe, particularly the cosmic microwave background, yield one value for a day's expansion rate. Methods based on nearby galaxies and supernovae produce a slightly higher value. This difference is known as the Hubble tension. It is not yet clear whether the discrepancy reflects unknown systematic errors, overlooked complexities in measurement, or entirely new physics. Researchers approach the problem with caution. Extraordinary claims require extraordinary evidence. At present, the Hubble tension remains an active scientific puzzle rather than a confirmed revolution. Its importance lies not in overturning everything we know, but in reminding us that cosmology remains a living science. Every generation inherits better instruments. Every generation asks sharper questions. Every generation discovers that nature is often subtler than expected. Perhaps nowhere is this more evident than in our original mystery. Despite observing galaxies across billions of light years, despite mapping ancient radiation released nearly 14 billion years ago, despite measuring gravitational waves, gravitational lensing, and the distribution of cosmic structure, modern astronomy continues to find no evidence for a unique center of the universe. Instead, every new observational tool strengthens the remarkable picture that has gradually emerged over the past century. And yet, for all these achievements, some of the deepest questions remain untouched. We know astonishingly much about the universe. We also know precisely where our understanding begins to fade. Beyond those boundaries lies one of the most fascinating frontiers in all of science. Not what we have discovered, but what we still do not know. One of the quiet strengths of science is that it does not pretend to know more than it does. Every major discovery has expanded humanity's understanding of the universe. Yet almost every discovery has also revealed new questions waiting beyond it. The more carefully astronomers observe the cosmos, the more clearly they can see the boundaries of current knowledge. These boundaries are not signs of failure. They are the frontiers that guide future discovery. It is tempting to think that modern cosmology has nearly completed its map of the universe. After all, we have measured the age of the observable universe to remarkable precision. We have detected planets around distant stars. We have photographed black holes. We have mapped galaxies across billions of light years. We have observed light that has travelled for nearly the entire history of the cosmos. Surely little mystery remains. The reality is almost the opposite. Some of the largest questions have become sharper than ever. Perhaps the most fundamental concerns the universe itself. We often speak confidently about the universe being approximately 13.8 billion years old. Strictly speaking, however, that statement refers to the observable universe as described by the standard cosmological model. It marks the time since the hot, dense early state from which the observable cosmos evolved. Whether that event represents the absolute beginning of everything remains unknown. General relativity allows us to trace cosmic history backward only to an extremely early period. As the universe becomes hotter and denser, quantum effects are expected to become increasingly important. Eventually, our current theories cease to provide reliable answers. This boundary is sometimes associated with the Planck epoch. an unimaginably early interval less than a trillionth of a trillionth of a trillionth of a trillionth of a second after the beginning of cosmic expansion. At such scales, both gravity and quantum mechanics are essential. Unfortunately, physicists still lack a complete theory combining them. This is not because scientists have stopped trying. For decades, researchers have explored approaches including string theory, loop quantum gravity, causal dynamical triangulations, and several other frameworks. Each offers intriguing possibilities. None has yet received decisive observational confirmation. As a result, one of the deepest questions remains open. What happened before the earliest moment our theories can successfully describe? The honest scientific answer is simple. We do not know. That uncertainty extends naturally to another mystery. Was the Big Bang truly the beginning, or merely the beginning of the observable phase of our universe? Some theoretical models propose an earlier contracting universe. Others suggest repeated cosmic cycles. Still others describe quantum processes in which space-time itself emerges from more fundamental ingredients. These ideas remain scientifically interesting. They also remain hypotheses rather than established conclusions. The evidence available today is not sufficient to choose confidently among them. Another great uncertainty concerns the overall size of the universe. The observable universe has a measurable radius because light has travelled for only a finite amount of time. Beyond that horizon, however, lies territory forever hidden from direct observation. Perhaps space continues infinitely. Perhaps it eventually curves back upon itself. Perhaps its global geometry is more subtle than either possibility. Current measurements indicate that observable space is extremely close to flat. Yet even perfect measurements within our observable region may never reveal the complete geometry beyond our horizon. Nature itself may impose permanent limits upon what can be known. This possibility can feel frustrating. Science often celebrates discovery. Less often do we reflect upon the questions that observation may never fully resolve. The horizon surrounding us is not merely technological. Even infinitely advanced telescopes cannot receive light that has not had time to arrive. Some regions of reality may simply remain forever inaccessible. That realization introduces an unusual kind of humility. It reminds us that knowledge depends not only upon intelligence, but also upon the structure of the universe itself. Then there is dark matter. For nearly a century, its gravitational influence has become increasingly difficult to ignore. Galaxy rotation curves, galaxy clusters, gravitational lensing, the cosmic microwave background, large-scale structure, independent observations repeatedly indicate that ordinary matter alone cannot explain the universe we observe. Yet despite decades of increasingly sensitive experiments, the fundamental identity of dark matter remains elusive. Scientists have searched for new particles deep underground, hoping to shield delicate detectors from ordinary cosmic radiation. Particle accelerators have attempted to produce candidate particles directly. Astronomical observations continue refining the properties that dark matter must possess. So far, the mystery remains. Dark energy presents an equally profound challenge. Observations indicate that it dominates the large-scale evolution of the universe today. Its effects are measurable. Its nature remains obscure. Is it a property of empty space? A dynamic field that changes over time? Evidence of physics beyond general relativity? Current observations constrain many possibilities, but no definitive answer has emerged. Another unanswered question concerns inflation. Earlier, we explored how a brief period of rapid expansion could explain several remarkable features of the observable universe. Many observations support predictions consistent with inflationary models. Yet one crucial mystery remains. What actually caused inflation? What physical field drove this extraordinary expansion? How did inflation begin? Why did it end? These questions remain active areas of research. The universe continues to guard its earlier secrets carefully. Even the expansion rate itself presents uncertainty. The Hubble tension, though subtle, reminds cosmologists that independent measurements do not yet agree perfectly. Perhaps improved observations will eventually reconcile the difference. Perhaps the discrepancy points toward new physics waiting to be discovered. Either outcome would deepen our understanding. Science does not fear disagreement. Carefully measured disagreement often marks the beginning of progress. There is another uncertainty that is quieter, but no less profound. The cosmological principle has proven remarkably successful. The universe appears homogeneous and isotropic on sufficiently large scales. Yet astronomers continue testing this assumption with ever larger surveys. Science never treats even its most successful ideas as beyond question. Every new observation becomes another opportunity to confirm, refine, or challenge existing understanding. This continual testing is one reason modern cosmology has become so reliable. Confidence comes not from certainty, but from repeated examination. Perhaps the most beautiful unanswered question returns us to the theme of this documentary. Why does the universe possess no preferred center? General relativity explains how such a universe can exist. Observations strongly support that description. But why should space-time possess these particular properties rather than others? Was it inevitable? Was it determined by conditions in the earliest universe? Could different universes, if they exist, possess entirely different geometries? At present, science offers possibilities rather than conclusions. The mystery remains open. Some people find uncertainty uncomfortable. Astronomers often find it inspiring. Every unanswered question represents an invitation rather than an obstacle. The universe is not diminished by what we do not yet understand. If anything, its mystery becomes richer. Each generation inherits both remarkable knowledge and remarkable ignorance. The balance slowly shifts, but it never disappears entirely. That may be one of the defining characteristics of science itself. Every answer opens another door, every horizon reveals another beyond it, and somewhere beyond today's horizon, at the very edge of observation and theory, lies the next great chapter in humanity's attempt to understand a universe that may never offer a final answer. Every map has an edge, not always an edge in the landscape itself, but an edge in knowledge. For ancient sailors, it was the point beyond which no reliable charts existed. For early explorers, it was the horizon where familiar coastlines disappeared into mist. For astronomers today, the frontier is not marked by mountains or oceans, but by the limits of observation itself. The remarkable thing about the universe is that these limits are not merely technological. Even with infinitely perfect telescopes, there are questions that may remain extraordinarily difficult, and perhaps impossible, to answer. This is one of the quiet lessons of cosmology. The universe does not simply contain mysteries. It also defines the boundaries within which those mysteries can be investigated. Consider the speed of light. In everyday life, light feels instantaneous. Sunlight floods a room the moment curtains are opened. A distant lightning strike appears almost immediately. Compared with the pace of human experience, light is unimaginably fast. Yet across the scale of the universe, even light has limits. It travels approximately 300,000 kilometers every second. That speed is enormous, but the universe is vastly larger still. When astronomers observe a galaxy 10 billion light-years away, they are not seeing that galaxy as it exists today. They are seeing light that began its journey long before the Earth had reached its present age. Everything we observe is history. Even the nearest stars belong to the past. This means that astronomy is fundamentally different from almost every other science. A geologist can examine a mountain as it exists now. A biologist can observe a living organism in the present. An astronomer can never see the distant universe as it is at this moment. The farther away something lies, the older the information becomes. This creates a remarkable limitation. Suppose there exists a galaxy whose light has been travelling toward Earth for 13 billion years. The image arriving tonight reveals only that ancient moment. Whatever has happened there since then remains invisible until newer light eventually reaches us. The present universe always lies slightly beyond our direct view. As distances increase, this separation between observation and reality becomes ever greater. Eventually, another boundary appears, the observable universe itself. Earlier, we described this as the region from which light has had sufficient time to reach us since the early universe became transparent. Everything beyond that horizon remains unseen, not because it does not exist, not because telescopes lack sensitivity, but because its light has not yet arrived. This horizon often creates misunderstanding. It is tempting to imagine it as a physical wall surrounding humanity. It is nothing of the sort. If another civilization exists billions of light years away, they possess a different observable universe centered upon their own location. Their horizon overlaps ours only partially. Both horizons are equally real. Neither represents the complete universe. The observable universe is therefore a limitation of perspective rather than a boundary in space. This distinction becomes even more intriguing when we consider cosmic expansion. As the universe grows, light emitted by extremely distant galaxies must travel through space-time that continues stretching while the journey is underway. For nearby galaxies, light easily overcomes this gradual expansion. For sufficiently distant regions, however, the situation changes. The space between us and those galaxies expands so rapidly that newly emitted light may never successfully bridge the growing distance. This does not violate Einstein's theory. Nothing locally travels faster than light through space. Instead, space itself continues expanding. The geometry evolves while the photons are already in flight. The consequence is extraordinary. Some regions of today's universe may remain permanently beyond future observation, not temporarily hidden. Forever unreachable, their ancient light may already be on its way toward us. Their present condition may never become visible. This idea introduces a kind of cosmic loneliness, though not necessarily a tragic one. It simply reflects the evolving geometry of space-time. The universe does not promise unlimited access to itself. Astronomers have learned to work gracefully within these constraints. Every observation becomes precious precisely because it cannot be repeated under different conditions. We cannot rewind cosmic history. We cannot rerun the universe with slightly altered initial conditions. There is only one cosmos available for study, one unfolding history, one opportunity to decode its ancient messages. Theoretical physics encounters its own frontier. General relativity has passed every experimental test with remarkable success across a vast range of conditions. Quantum mechanics has proven equally successful within the microscopic world. Yet when physicists attempt to describe situations where both theories become equally important, difficulties arise. Black hole singularities, the earliest instance of cosmic history, extremely high energy conditions, our mathematical descriptions begin to lose their predictive power. This is not because nature has become irrational. Rather, it suggests that our present theories describe different aspects of a deeper reality that remains only partially understood. For decades, physicists have searched for a more complete framework. Some approaches envision tiny vibrating strings replacing point-like particles. Others describe space-time itself as emerging from discrete quantum structures. Still others explore entirely different mathematical foundations. Each seeks the same goal, a theory capable of describing gravity and quantum physics simultaneously. Such a theory would not merely solve an abstract mathematical puzzle. It might reveal what happened before inflation. It might explain why space-time possesses its observed geometry. It might even clarify why the universe appears to have no preferred center at all. Yet honesty requires acknowledging that such breakthroughs have not yet arrived. The frontier remains open. Perhaps the greatest challenge, however, is philosophical rather than technical. How do we distinguish between questions that are temporarily unanswered and questions that may never admit observational tests? Science depends upon evidence. A beautiful idea unsupported by observation remains speculation. Conversely, an unexpected measurement can overturn decades of confident assumptions. This discipline has protected astronomy from drifting into fantasy. It has also encouraged patience. Not every mystery yields its answer immediately. Some require generations of improved instruments. Others require entirely new ways of thinking. History repeatedly demonstrates this pattern. The motion of planets once seemed impossibly complex until heliocentrism simplified the picture. Gravity remained mysterious until Einstein reimagined space-time. Perhaps today's deepest puzzles await similarly elegant insights, or perhaps the universe will always preserve certain secrets. There is a quiet dignity in accepting that possibility. The value of science has never depended upon possessing every answer. Its strength lies in asking better questions. Each telescope extends our vision. Each spacecraft broadens our reach. Each generation carries the frontier slightly farther than the one before. Yet the horizon never disappears. It simply moves. And standing at that moving horizon, astronomers continue searching for clues that may reshape everything once again. For beyond today's edge of knowledge lies not emptiness, but the possibility that the universe is even stranger, more subtle, and more beautiful than our current understanding allows. The longest journeys often end where they began, not because nothing has changed, but because the traveller has changed. The landscape remains the same. The meaning of the landscape does not. Our journey through the universe has followed a similar path. We began with a question that seemed almost obvious. Where is the center of space? At first, it appeared to be a simple matter of finding the correct location, somewhere beyond the Milky Way, perhaps beyond the great galaxy clusters, some distant point from which everything else had expanded. Now that question has quietly transformed into something much deeper. What if the universe is not the kind of thing that can possess a center at all? That possibility does more than alter astronomy. It changes how we think about reality itself. Human beings naturally understand the world through position. We know where we live. We know where north lies. We know the center of a city, the center of a country, even the center of a hurricane. Location provides meaning. Our language is built around it. Our maps depend upon it. Our intuition expects every journey to begin somewhere and every object to have a middle. Yet the universe continues asking us to separate local experience from universal truth. Locally, centers remain everywhere. The Earth has a center. The Sun has a center. The Milky Way has a dense galactic core. Galaxy clusters possess gravitational centers around which their members orbit. None of these facts has changed. What changes is our understanding of the universe as a whole. The universe is not simply the largest object inside a larger environment. According to everything modern cosmology has measured, it is the very framework within which objects exist. That distinction is subtle. It is also profound. Imagine asking for the location of the beginning of a story. The question works perfectly if the story is a printed book. The first page exists. The first sentence exists. But if someone asks where the beginning of language itself is located, the question becomes more difficult. Language is not an object occupying a particular place. It is a system. Likewise, space-time is not merely another object within reality. It appears to be part of the structure that makes physical reality possible. This realization has quietly reshaped philosophy as much as physics. For centuries, many thinkers viewed space as an empty container. Matter occupied the container. Stars moved through it. Galaxies drifted inside it. General relativity overturned that picture. Space became dynamic. It stretches. It curves. It responds to matter and energy. Time itself joins this geometry, forming the unified space-time that governs the evolution of the cosmos. Once space becomes dynamic, familiar questions begin changing their meaning. Where is the center of expansion? The question assumes expansion occurs inside something else. Current observations suggest otherwise. Where is the edge of space? Again, the question assumes space behaves like an object with boundaries inside a larger arena. Nothing observed so far requires such an arena. This shift resembles another profound change in scientific history. When Copernicus proposed that Earth orbits the Sun, he did not merely move planets around a diagram. He changed humanity's perspective. When Einstein described gravity as geometry, he did not simply improve Newton's equations. He transformed the meaning of space and time. Likewise, realizing that the universe may have no center changes more than cosmology. It changes the questions we ask. Instead of asking where the universe is centered, astronomers ask how its geometry evolves. Instead of searching for a privileged location, they search for universal laws that operate everywhere equally. In many ways, this is one of the deepest principles in modern science. The laws of physics appear astonishingly democratic. The same hydrogen atom behaves identically whether it exists inside a laboratory on Earth or within a distant galaxy billions of light years away. Gravity bends light according to the same equations throughout the observable universe. The spectra of distant stars obey the same atomic physics measured here on Earth. This universality makes astronomy possible. If physical laws change dramatically from place to place, interpreting distant observations would become nearly impossible. Instead, every successful observation strengthens the remarkable conclusion that the cosmos follows common principles across unimaginable distances. There is something quietly beautiful about this. Although humanity occupies no privileged location, we participate in a universe whose rules appear shared everywhere. The atoms inside our bodies formed within ancient stars. The same nuclear reactions illuminate distant suns. The same gravity guiding planets around those stars governs the motion of galaxies themselves. The absence of a cosmic center does not make the universe feel empty. It makes it feel connected. Every location belongs to the same unfolding history. Every observer studies the same physical reality from a different perspective. This idea also offers an unexpected answer to a concern that sometimes arises when discussing cosmology. If humanity is not central, does that make us insignificant? Science offers no direct answer to questions of meaning, yet it reveals something equally valuable. Importance and centrality are not the same thing. The heart occupies the center of neither the human body nor the solar system. Its importance comes from function, not position. Likewise, the significance of conscious beings need not depend upon living at the geometric center of existence. Indeed, one of the most extraordinary facts about the universe is that tiny collections of atoms on an ordinary planet have become capable of understanding galaxies billions of light years away. That achievement does not require occupying a privileged location. It requires curiosity. Throughout history, every step away from cosmic centrality has also brought humanity closer to a deeper understanding of reality. Losing the center has repeatedly expanded the universe. Earth became one world among many. The Sun became one ordinary star. The Milky Way became one ordinary galaxy. Now the observable universe itself appears as one local window into something vastly greater. Each step has reduced our apparent importance while increasing the grandeur of the cosmos. Perhaps those two changes are not opposites after all. Perhaps they are partners. The universe becomes more astonishing precisely because it refuses to revolve around us. And yet one final mystery remains. If every observer sees themselves surrounded by an expanding universe, if every location obeys the same physical laws, if space itself possesses no preferred center, then what, if anything, ultimately defines our place within such a cosmos? That question belongs not only to astronomy, but to every thoughtful observer who has ever looked upward beneath a quiet night sky. Every civilization has looked toward the future. Ancient farmers watched the seasons. Sailors studied the tides. Astronomers measured the slow motions of the heavens. The future has always been uncertain. Yet nature often reveals enough regularity to allow careful prediction. Cosmology follows the same tradition. By understanding how the universe behaves today, scientists can ask how it may behave billions, trillions, or even unimaginably longer spans of time from now. Unlike many discussions of the future, however, cosmology proceeds with unusual caution. Some predictions rest upon extremely well-tested physics. Others depend upon observations that remain incomplete. Still others explore possibilities whose likelihood cannot yet be determined. Keeping these distinctions clear is essential. One prediction enjoys overwhelming scientific confidence. The universe will continue expanding for the foreseeable future. For much of the 20th century, astronomers expected gravity to slow this expansion. After all, every galaxy attracts every other galaxy. Even if expansion continued forever, it seemed reasonable to expect the rate to decrease gradually. Then, toward the end of the 1990s, observations of distant Type Ia supernovae revealed something unexpected. Expansion is accelerating. Whatever dark energy ultimately proves to be, its influence appears to dominate the universe on the larger scales today. If future observations continue supporting this picture, then the universe will become increasingly isolated. The local group provides a useful example. Gravity has already bound the Milky Way, Andromeda, and numerous smaller galaxies together. Their mutual attraction is strong enough to overcome cosmic expansion. Several billion years from now, the Milky Way and Andromeda are expected to merge into a single giant galaxy. The night sky will change dramatically. The familiar spiral band of the Milky Way will gradually transform as enormous streams of stars arc across the heavens. Individual stars will almost certainly remain extraordinarily far apart. Direct stellar collisions are expected to be rare. Instead, gravity will slowly rearrange hundreds of billions of stars into a new galactic home. Yet beyond our local group, the story unfolds very differently. More distant galaxy clusters will continue drifting away. As expansion accelerates, their light will become increasingly stretched toward longer wavelengths. Eventually, many galaxies visible today will fade beyond the reach of future observers, not because they disappear, not because they cease to exist, but because expanding space continually increases the distance between them. Imagine standing on a shoreline while boats slowly drift toward the horizon. One by one they become smaller. Eventually they vanish from sight. The boats continue their journeys. Your ability to observe them simply ends. Future astronomers may experience something similar on a cosmic scale. Trillions of years from now, if dark energy continues behaving as current observations suggest, civilizations inside our merged galaxy may find themselves surrounded by apparent emptiness. Nearly every external galaxy could lie beyond their observable horizon. Ironically, future scientists might struggle to discover that the universe is expanding at all. Many of the clues available to us today would no longer be visible. This possibility is one of the more thought-provoking consequences of modern cosmology. We happen to live during an era when the expansion of the universe remains observable. That window may not remain open forever. There is another prediction supported by well-established stellar physics. Stars themselves have finite lifetimes. The Sun will continue fusing hydrogen for roughly another 5 billion years before evolving into a red giant. More massive stars exhaust their fuel much more quickly. Smaller red dwarfs burn far more slowly and may continue shining for trillions of years. Eventually, however, even the longest-lived stars will exhaust their nuclear fuel. The brilliant age of starlight will gradually fade. Galaxies will become populated primarily by stellar remnants. White dwarfs, neutron stars, black holes. The universe will grow darker, not suddenly, but with extraordinary patience. Beyond that point, predictions become increasingly speculative. Physicists sometimes describe a possible future called the heat death of the universe. Despite the dramatic name, it involves no catastrophic explosion. Instead, it represents an extremely distant era in which usable energy becomes increasingly scarce. Stars have long ceased forming. Existing stars have faded. Matter slowly decays or becomes locked within compact remnants. Depending upon the behavior of particles over immense spans of time, entropy, a measure closely associated with the dispersal of energy, continues increasing. The universe approaches a state of extraordinary uniformity. Heat death remains one scientifically plausible long-term scenario if current understanding of dark energy and particle physics proves correct. Yet several uncertainties remain. For example, scientists do not yet know whether protons are ultimately stable. Experiments have searched for proton decay without confirming it. If protons eventually decay, ordinary matter itself would gradually transform over astonishingly long periods. If they remain stable indefinitely, the distant future unfolds somewhat differently. Likewise, the ultimate behavior of dark energy remains uncertain. Current observations are consistent with a cosmological constant, implying that acceleration continues indefinitely. Other possibilities remain under investigation. If dark energy evolves over time, the universe's future could differ significantly from present expectations. Some speculative models even propose scenarios in which acceleration eventually reverses or becomes dramatically stronger. The latter possibility has sometimes been called the Big Rip. In such models, expansion would ultimately become powerful enough to separate galaxy clusters, galaxies, stars, planets, and eventually even atoms. It is important to emphasize that current observations do not require this outcome. It remains one theoretical possibility among several. Most evidence presently favors a more gradual, continuously expanding future. The future also raises philosophical questions that science alone cannot answer. Suppose intelligent civilizations survive for billions or trillions of years. How would their understanding of the universe differ from ours? Would they infer cosmic expansion if nearly every distant galaxy had disappeared beyond observation? Would they reconstruct the Big Bang from the remaining evidence? Or would they develop entirely different cosmological theories based upon a much quieter sky? These questions remain speculative, yet they highlight an important truth. Scientific knowledge depends not only upon intelligence, but also upon the information available to observers. Humanity occupies one particular moment in cosmic history. Our observations reflect that moment. Future observers may inherit different evidence and therefore confront different mysteries. Perhaps the most remarkable aspect of all these predictions is their relationship to our original question. Whether galaxies merge or drift apart, whether stars continue shining or eventually fade, whether expansion persists forever or follows some more complicated path. None of these possibilities introduces a cosmic center. The future universe remains consistent with the same extraordinary geometry we have followed throughout this journey. Space expands, Observers remain locally central only within their own observable horizons. The universe itself continues offering no preferred location. Its future, like its past, unfolds everywhere at once, and after contemplating trillions upon trillions of years, there remains one final step. Not another prediction, not another theory, simply a return to the quiet question with which our journey began. Now seen through eyes that have travelled much farther than they once imagined, at the beginning of our journey, the question seemed almost effortless. Where is the centre of space? It felt like the sort of question that should have a straightforward answer. Somewhere, beyond the stars and beyond the galaxies, there must surely be a location that deserves to be called the middle of everything. Now, after travelling across billions of light years and nearly 14 billion years of cosmic history, the question sounds subtly different. Not because the words have changed, because we have. One of the remarkable qualities of science is that it rarely answers a profound question in the way we first expect. Instead, it often transforms the question itself. Centuries ago, people asked why the sun moved around Earth. The eventual answer was not a better description of the sun's path. It was the realization that Earth itself was moving. Likewise, astronomers once searched for the center of the universe. What they gradually discovered was that the universe may not be the kind of reality that possesses a center in the ordinary sense. This change in perspective is easy to overlook because it happened slowly. No single observation overturned the old picture overnight. Instead, every generation contributed another piece. Copernicus showed that Earth was not the center of the solar system. Galileo's telescope revealed worlds beyond our own. Newton described gravity with astonishing precision. Einstein transformed gravity into geometry. Hubble revealed an expanding universe. Penzias and Wilson uncovered the ancient glow of the cosmic microwave background. Modern observatories mapped billions of galaxies. Each discovery seemed to address its own particular mystery. Together, they quietly rewrote humanity's place in the cosmos. Notice what has happened throughout this history. At every stage, the universe has become larger, more complex, more beautiful, yet our position within it has become less exceptional. This pattern has sometimes been called the Copernican principle in its broadest philosophical sense, not the specific historical proposal that Earth orbits the Sun, but the deeper idea that we should not assume our location occupies a privileged place unless evidence demands it. Again and again, the evidence has pointed in the opposite direction. The laws of physics appear universal. The large-scale universe appears remarkably uniform. The expansion of space appears the same from every sufficiently distant galaxy. No hidden center has emerged despite generations of increasingly sophisticated observations. This conclusion can initially feel disappointing. Human beings naturally enjoy occupying important places. Ancient maps often placed their own kingdoms at the center. Early cosmologies placed Earth at the center. Even today, maps are usually drawn with one's own nation near the middle. Perspective quietly shapes identity, yet astronomy offers a different kind of significance. Instead of importance through position, it reveals importance through participation. Every atom in your body shares a common cosmic history. The carbon in your cells was forged inside long-vanished stars. The oxygen you breathe was assembled through nuclear reactions that occurred billions of years before Earth existed. The calcium within your bones originated in stellar explosions that enriched interstellar clouds from which new generations of stars and planets eventually formed. Nothing about that story depends upon occupying the center of the universe. It depends only upon belonging to it. This realization dissolves another subtle misconception. The absence of a cosmic center does not imply disorder. Quite the opposite. The universe displays extraordinary coherence. Gravity behaves consistently. Light follows the same physical principles everywhere we observe. Atomic spectra remain identical across billions of light years. The same mathematical relationships describe galaxies both nearby and unimaginably distant. Order exists. It simply arises from universal laws rather than from a preferred location. Perhaps this is the deeper lesson hidden within our original question. Sometimes we seek structure in the wrong place. We expect order to come from hierarchy, from centers, from boundaries. Nature often creates order differently. Snowflakes grow without central architects. Galaxies form through countless local interactions guided by gravity. The cosmic web emerges from tiny fluctuations amplified over billions of years. The universe achieves harmony through shared rules rather than privileged positions. There is another perspective worth considering. Throughout this documentary, we have repeatedly used words such as everywhere, every direction, and the universe. These expressions are convenient, yet they also conceal the limits of our knowledge. Strictly speaking, almost everything discussed concerns the observable universe. That distinction has accompanied us from the beginning, even when left unstated for the sake of narrative flow. Beyond our observable horizon may lie vastly more space, perhaps infinitely more. Current evidence cannot determine its full extent. What matters is that within everything available to observation, the same remarkable pattern continues to appear. No preferred center, no privileged direction, no sign that our location occupies a special geometric status. Science is careful here. It does not claim certainty beyond evidence. It simply follows where the observations lead. This willingness to remain faithful to evidence, even when it challenges intuition, has become one of humanity's greatest intellectual achievements. The universe has repeatedly invited us to surrender comforting assumptions. In return, it has offered something far richer. Reality, not simplified, not always intuitive, but astonishingly consistent. There is a quiet symmetry in this exchange. The more humanity has relinquished the idea of occupying the center, the more deeply we have come to understand the universe that surrounds us. Perhaps understanding itself is the greater privilege. After all, among the countless galaxies scattered across the observable cosmos, we know of only one small world where the universe has become aware enough to ask questions about its own geometry. Whether others exist remains unknown. Whether they ask the same questions remains unknowable. But if they do, they may eventually discover what we have discovered, that standing at the apparent center of their observable universe does not make them special. It makes them participants in the same magnificent cosmic story. And now, having travelled from ancient intuitions to modern cosmology, only one step remains. Not another measurement, not another equation, only a quiet moment to consider what it means to live within a universe whose greatest mystery was never the location of its centre, but the realization that it may never have needed one at all. The night sky has not changed while we have been travelling. The same stars still rise above familiar horizons. The Milky Way still stretches across the darkness where the air is clear enough to reveal it. The Andromeda Galaxy still drifts silently toward its future meeting with our own. Nothing overhead appears different, and yet perhaps everything does. At the beginning of this journey, the universe seemed like an immense object waiting to be explored. It felt natural to picture it as something similar to the things we know best. A great sphere, a vast cloud, an unimaginably large explosion whose centre simply lay beyond our reach. Those images were comforting because they belonged to the language of ordinary experience. Now they seem a little less certain, not because they were foolish, because the universe has gently invited us to think beyond the habits of everyday life, again and again. Astronomy has revealed that reality often becomes stranger as our perspective grows larger. The Earth feels still, yet it moves around the Sun. The Sun feels unique, yet it is one ordinary star among hundreds of billions. The Milky Way once seemed immense enough to contain everything, yet it became one galaxy among countless others. Each step outward has carried the same quiet lesson. The universe is usually larger than our first understanding of it. Perhaps that is why the question of a centre has remained so compelling. A centre promises certainty. It offers orientation. If there is a middle, then every other place can be measured from it. Maps become simpler. Distances become meaningful in familiar ways. Our minds naturally long for such order. Yet the cosmos appears to offer another kind of order, not the order of a kingdom organized around a capital, not the order of a wheel turning around its hub. Instead, it offers the order of universal law. Wherever astronomers have looked, the same gravity shapes the motion of galaxies. The same atoms absorb and emit the same wavelengths of light. The same expansion unfolds across the observable universe. The same ancient microwave glow surrounds every direction. The harmony comes not from a privileged place, but from shared principles. There is something quietly reassuring about that. The universe does not appear to favour one location over another. It does not reserve different laws for distant galaxies. The physical rules that guide the birth of stars in a galaxy billions of light years away appear to be the very same rules that once shaped our own sun. The chemistry that assembled the molecules of life here on Earth is written into the spectra of distant nebulae, across distances so immense that language struggles to describe them. The universe behaves with remarkable consistency. Perhaps this is why astronomy often inspires a feeling that is difficult to name. It is not merely curiosity, nor is it simply wonder. It is the realization that we belong to something whose scale exceeds imagination while remaining comprehensible, at least in part, through patient observation and careful reasoning. The universe never promised to be simple. It has, however, proven to be understandable. Not completely, not finally, but enough that beings living on a small rocky planet can reconstruct events that occurred nearly 14 billion years ago. Enough that we can measure the expansion of space itself. Enough that we can detect light released before stars even existed. That achievement is extraordinary. It is easy to focus on the mysteries that remain. Dark matter, dark energy, the earliest moments of cosmic history, the true extent of the universe beyond our observable horizon, the ultimate union of gravity and quantum mechanics. Each remains unresolved. Each will likely occupy generations of scientists yet to come. But there is another way to view these mysteries, not as empty spaces in our knowledge, as invitations. Every unanswered question is evidence that the universe is still capable of surprising us. Every unexplained observation reminds us that discovery is not finished. Every new telescope extends the conversation a little farther into the darkness. History suggests that future astronomers will inherit questions we cannot yet imagine, just as we inherited questions that would have seemed impossible to ancient skywatchers. Perhaps one day a deeper theory of gravity and quantum physics will emerge. Perhaps new observatories will detect signals from the universe's earliest fractions of a second. Perhaps the nature of dark matter will finally be revealed. Perhaps the apparent acceleration of cosmic expansion will acquire a simple explanation that seems obvious in hindsight. Or perhaps each answer will simply reveal another layer beneath it. Science has followed that pattern for centuries. The horizon retreats as we approach it. The unknown does not disappear. It becomes more refined. There is a quiet beauty in that endless progression. Knowledge is not a destination. It is a path. One observation leading to another. One question unfolding into the next. One generation extending the work of those who came before. The universe itself seems to encourage this way of thinking. It does not end abruptly. Its history flows continuously from the first detectable light to the galaxies of today and onward, into a future measured in trillions of years. Every moment becomes part of a larger story. Our own lives occupy only an instant within that immense timeline. Yet for a brief moment, the universe has produced creatures capable of wondering about its own nature. That may be among the rarest events we know, not because humanity stands at the center of existence, but because consciousness allows the universe, however briefly, to observe itself, perhaps somewhere beyond our observable horizon. Another civilization has looked upward beneath an unfamiliar sky. Perhaps they have measured distant galaxies. Perhaps they have discovered the same ancient microwave background. Perhaps they too have wrestled with the strange realization that every direction appears equally ordinary, that every observer seemed quietly central, and yet no true center can be found. If so, their journey would resemble ours more closely than either civilization could ever know. They would discover, as we have, that perspective can be universal without being unique, that the absence of a center is not a flaw in the universe. It is one of its defining characteristics. And so we return, at last, to the question with which we began: where is the center of space? Modern astronomy offers a remarkable answer. Not hidden beyond the most distant galaxies, not concealed outside the observable universe, not waiting to be discovered by a more powerful telescope. The question itself slowly dissolves as our understanding grows. The universe does not seem to require a center in order to possess structure. It does not require a privileged location in order to possess order. It does not require a cosmic middle in order to contain every galaxy, every star, every planet, and every observer who has ever wondered about their place among them. Perhaps that is the quietest lesson of all. Sometimes the deepest understanding does not come from finding the answer we expected. It comes from discovering that reality has been asking a different question all along. and somewhere beyond the faintest galaxies we can ever hope to observe, beyond the horizon where light itself has not yet arrived, the universe continues its silent expansion, inviting future generations to ask one more question that no telescope has yet answered. If space has no center, then what other assumptions about reality are still waiting, patiently, for us to leave behind?